Here are motion graphs for the idealised situation of throwing an object vertically upwards in the case of no drag, which is not that realistic, and constant gravitational field strength, which is pretty realistic if we're unable to throw it many kilometres into the air. If we're measuring positively in the upward direction, as suggested by the graph axes, then the acceleration has a constant value of negative 10 metres per second squared, because it's acting downwards. Let's say we throw it upwards at 15 metres per second, then v starts at 15 and immediately starts to decrease uniformly by 10 each second, because the acceleration is minus 10, which means in this case 10 in a downward direction. So after 1 second the value of velocity is 5 metres per second, and after 1.5 seconds its value is 0. Notice that the area bounded by the acceleration over 1.5 seconds is 1.5 multiplied by minus 10 or minus 15 metres per second, which is precisely the change in velocity discussed. In other words, integrating the acceleration function gives the velocity change. Where is the ball? At the top of its motion. And how far above its starting position is it? Well, that's given by the area under the velocity curve, half of 1.5 times 15, or 11.25 metres. What happens to the velocity from that point on? Well, it continues to decrease, and if it decreases from 0, it becomes negative. 3 seconds after it was thrown, it lands with a velocity of minus 15 metres per second. This is the same speed, 15, with which it was launched, but not the same velocity. The negative sign signifies that it's travelling in the opposite direction. Speed is a scalar quantity and velocity is a vector, so speed is blind to the direction of travel, whereas the difference between the starting and ending velocities is 30. We could draw a speed time graph rather than a velocity time graph. It would look like this. Notice how the speeds are mirrored in the two halves of the motion. What about the displacement? Well, we could integrate the velocity time graph and we would get a parabola like this. The gradient of the parabola is equal to the velocity, so you should hopefully see that the decreasing gradient in red corresponds to the decreasing value of velocity in orange. We already know that the maximum displacement is 11.25 metres at the top of the motion, that is, at t equals 1.5 seconds, and at t equals 3 seconds its displacement, which is a vector quantity, is 0 because it has returned to its starting point. Is there a corresponding scalar quantity for displacement in the way that speed corresponds to velocity? Well, yes. It's the total distance travelled. No direction, just an amount of distance. And after 3 seconds it's 22.5 metres. 11.25 metres there and 11.25 metres back again, although the displacement after 3 seconds is 0. In this graph we've had to change scale to fit it on the page. These 2 points are equivalent. And finally, it's worth pointing out that the parabolic curve does not represent the trajectory of the ball through space. We are launching it vertically and plotting its vertical displacement against time. That's an easy point of confusion because that shape is exactly what its trajectory would look like if we relabeled the axes as horizontal and vertical displacements and then launched the ball at an angle to the horizontal.